So ionization is when a covalent substance forms ions. Bless you. Dissociation is when an ionic compound breaks into its ions. So an example of ionization would be hydrochloric acid going to hydrogen ions and chloride ions. An example of dissociation would be sodium chloride going to sodium ions and chloride ions. So ionization happens when you shouldn't normally or you wouldn't normally form ions. So hydrogen chloride gas, if it's dry, will not ionize. When it's wet, it forms hydrochloric acid and then it ionizes. So this thing here, this species, this entity, is called a hydrogen ion. And it is also called a proton. So you'll see those two words used to describe the H+ ion. Call it a proton. We also call it a hydrogen ion. And it's really important for acids. So Arrhenius said that an acid has an H in its formula and it ionizes in water to produce a hydrogen ion. So he said that's what we get. And a base had to contain OH-, and it will dissociate in water to form OH-. So under his definition, the only things that were bases were hydroxides. They already contained the OH in their formula. So for bases, if you make OH-, the hydroxide ion, you're basic. But this is a problem. This doesn't really hold to what we know because in water, we don't actually make H+ ions. We actually make something called the hydronium ions. So this is problem number one. Acids actually form H3O+, not H+. We make this entity H3O+, and this is called, and this is on your sheet, the hydronium ion. So basically, this first equation that you've got in your piece here under problem one, this, you can write this, but this is now considered to be an informal way to write the ionization of an acid. So this is informal. The formal way is the way that's represented underneath, hydrochloric acid, actually reacts with the water, and we make hydronium ions and chloride ions. So this is formal, and this is on your sheet. So basically, these two species are used interchangeably. We're going to use both ways. But if I ask you to write the ionization of an acid, you can do either way unless it specifically says formal or informal, okay? So, conjugate acid-base pairs are two substances, and they only in their formula by an H+. Do these differ in the formula? By an H+. I add an H+ to one of them. Does it make the other? Somewhere over here I've got an H+. If I add that to one of those two species, does it make the other one? Yeah? Sure? No? What happens if I add an H+ and an OH- together? What happens to the charge? It's neutral, and what does the formula become? H2O. So this is a conjugate acid-base pair because they differ in formula by an H+. How about this one? Is this a conjugate acid-base pair? Yeah? Yeah, no, maybe? How about this one? Does this differ in formula by an H+? Tamara is shaking her head. Saeed, what do you think? You're sort of, well, maybe, but I'm not sure how to say it. Okay. Yes or no? Conjugate acid-base pair or not? You're saying yes? You're saying yes? You are absolutely wrong. They differ in formula by an H and a sodium. There's no Na. Okay, so this is not a conjugate acid-base pair, but how about this? How about that one? Is that a conjugate acid-base pair? Yes. Do you know what they're called? That's acetic acid or ethanoic acid because it has two carbons. And this is called the acetate ion or the ethanoate ion. So those are conjugate acid-base pairs. How about are these conjugate acid-base pairs? Yes?
Yes.
Yes, they differ in formula by an H+. So these are. Okay. So turn the page. We're going to identify the conjugate acid-base partners and name them. So is this formal or informal? This is formal. So who's acting as an acid? Who's the acid in this? Who's giving up an H+? And what's it called? What do we call HC2H3O2?
That's a good question.
We just named it.
It's
Ethanoic acid. So, this is our acid. An acid is going to react with a base. So you've got a giver, you've got to have a taker. This gives up its proton. The other substance on the left-hand side will receive the proton. So you've got an acid and a base. Now we need to find their conjugate partners. So who's conjugate partner? H2O and H3O are conjugate partners, and ethanoic acid and ethanoate are conjugate acid-base partners. So we connect them, and if acetic acid is our acid, that means our acetate or our ethanoate ion is the conjugate base. If water is our base, the hydronium ion is our conjugate acid. If you are a very strong acid, you will have a very weak conjugate base. If you are a very strong base, you will have a very weak conjugate acid. So its conjugate partner will be the opposite in strength.
Why are they both like a C? Conjugate. Oh, okay.
See, you guys were too busy talking. So, now, why are you believing me that C2H3O2 is a conjugate base? Because I'm the teacher. Do you not care whether or not I'm right?
Yes.
What will this do in water? Water is either going to act as an acid or a base.
Is that one going to steal it and become ethanoic acid?
Yes, that's exactly what it's going to do. If it steals an H from water, what's left?
Acid.
What's left from the water? If it took an H plus, what's left?
OH.
An OH minus. Okay? This took an H from this to make that. So this ion produces this ion. This means it's making a base. So therefore, that is basic. That's how it's a conjugate base, because it will form hydroxide ions with water. See that? So if you have an acid, its partner will be a conjugate base, because when it reacts with water, it will produce hydroxide. Guess what? This is going to give up. It's going to give up an H plus. This is kind of weird, but it's kind of weird. This one, maybe we have a different base, but it will give up its hydrogen ion. Let's do this. H3O plus ammonia. It will give up its H plus. Okay, it will give up its H plus. Have this, you could have NH3. It's not very likely. That's what you would get if NH3 was acting as an acid, right? It would have to lose an H plus. So it would go down an H and go down a plus charge. So that's the base. That makes that the conjugate acid. And that makes that the conjugate base. So if you're an acid, your H plus, your other side becomes the conjugate opposite. So you're going to have some practice on this. Okay? It's good. It's good to know what we know. What is it? It's 14. Your pH scale runs from 0 to 14. Guess where we get the 14 from? It's amazing how everything's related. There's a reason for everything. There's a reason why your pH scale goes up to 14. And it's because of this relationship right there.
14.
No, water is not 14.
If water was 14, I'd be able to drink it.
Well, yeah, you would die after drinking it. It is actually possible to have a base a little bit higher than 14 and an acid a little bit lower. They're called superacids and
But they come
superbases.
naturally like that?
Yeah, you have to drink them. It's stronger.
So, we're going to use this when we talk about pH. So that's a story for another day.